All right, AP students, welcome to your AP problem walkthrough regarding periodic trends. And I'm going to also throw in a little bit of electron configuration because it's so integral to understanding the periodic table as well. So remember, we start off with conceptual. I will put a marker of when the AP problem starts that I have full fair game to check anytime at any point, then whether you did it. But let's go ahead and look at the conceptual. And if you want to skip on forward to the AP part, feel free. So question 31, page 8 in your workbook, unit 1 workbook. I ask you the question. You are given the cation magnesium 2 plus. Explain the difference between this cation and its neutral state. So first and foremost, the electron configuration of magnesium, let's just go standard magnesium, all right, is the following. Let's go ahead and pull up our periodic table. Magnesium is, okay, magnesium is, let me kind of clean this up a little bit for you. Okay, it is this element right here. And so when we think about electron configuration, what we have to realize is that we are writing out the address of each electrons in the distribution within the atom. And so what we do is with the electron configuration is we focus on the quantum principal numbers, the first quantum principal number, and then the angular momentum number, or the energy level and the orbital. So what we say is, well, I know that magnesium neutral has to have 12 electrons if it has 12 protons, right? Atomic number 12. And so we know that according to Aufbau principle, we fill from the ground up. So we start with row 1, orbital S, and we fill both of them. 1s2. Now, remember, hydrogen and helium are very special because they're kind of actually misplaced in a sense. When we look at the table, we feel like they're misplaced. However, we're going to soon find out that it's their electron count that wins out of why we put them where they are. But either way, across the span of the periodic table is still the 1s, energy level and orbital. And then we say, okay, that's 2 out of the 12 electrons placed from the lowest energy up. And let's continue to fill. So we go 2s2, 2p6, still not quite at magnesium. 10 out of my 12 electrons have been placed. And then it's 3s2. And now I am at where magnesium should be. And I filled all the seats in between, or all the electron vacancies have been filled with the 12 electrons that I need. And I go back to my thing and I say, okay, well, the standard magnesium atom has 1s2, 2s2, 2p6, 3s2 configuration. But when I look at 2 plus, okay, when I think about it being a cation, I know that if it's a cation, it's going to lose electrons. All right. It's not going to gain protons because that would make it a different element. So it's going to lose electrons. And we always take from the valence or highest energy level. So I'm actually going to take away these 2 electrons in the 3s orbital. And what I get left with is that my electron configuration for cation Mg2 plus is isoelectronic with neon. It has the same configuration as neon, 1s2, 2s2, 2p6. So what we see is that for the cation, okay, the atomic radius is going to shrink. Okay, it's going to get smaller because we have just lost electrons, the main source of volume. We have just lost 2 electrons in the energy level 3, main source of volume. And now our atom, our magnesium 2 plus cation, is going to only have a volume that extends up to energy level 2. We also see that the electronegativity, the ability to attract an electron to itself, is actually going to increase. Because now what we see is we have greater Coulombic attraction, okay, due to the fact that we have more protons, the muscle of the pole, the muscle behind the attraction, compared to the electrons present. We're also going to see that ionization energy increases because, again, the Coulombic attraction has increased, which means it is now going to be harder to pull, or I should say remove, more electrons. if you're a cation, you really don't want to lose any more electrons. Like there's a reason you're a cation, right? Notice that magnesium 2 plus is isoelectronic with a noble gas, neon. It has a full S&P orbital now. It is a full octet. So that was a loss that gave it stability. That those 2 electrons being lost gave it a new sense of stability, a new sense of energetic favorability, and electron arrangement favorability. But if you were to remove any more, it would be destabilizing. So what we see is that the ionization energy increases not only because of Coulombic attraction, but because of the octet rule. What we already know to be true is that elements want to become like a noble gas from the electron configuration point. They want to become isoelectronic with noble gases. So that's kind of the general trends. Let's go ahead and move down our page. And I think I might have, oh, maybe no more conceptual. And let's go ahead and hop into the AP portion. So we're going to address question 1, short FRQ. Remember, that's supposed to be about 9 minutes according to the AP. And we're just going to do part D. Explain why calcium, Cl2 or calcium chloride, calcium, Cl2 or calcium chloride. Don't forget, when you do problems, let them teach you more than just what they're asking you. Let them teach you how to say the compound name. Let them teach you how to identify patterns in ionic versus covalent, right? So explain why calcium chloride is likely to have properties similar to those of calcium bromide. Okay, so we know that according to the periodic law, and to, if you want to make it more casual, the periodic table organization. Okay, according to periodic law, it states that atoms, or really elements, because atoms are just naming one type, one subparticle, right? Like, or not even subparticle, one microscopic particle, but an element is talking more about the identity of that atom. So we say that the periodic law states that elements in the same column have similar properties due to similar electron arrangements. Particularly, what we really mean by that is, right, the same amount of valence electrons. Okay, that's the real focus. So bromine and chlorine are both halogens and would demonstrate similar properties. Okay. Okay, so that's kind of that one. Let's go ahead and move on to our next question, which is, we're going to skip over 2. You're most likely your job will be to finish number 2. You could totally do 2B and 2C on your own. You can finish this question. Remember to get the 10% curve. One, you have to do corrections, but to get the next 10%, so for a full 20% curve, you have to complete all AP problems in a workbook. Okay, so I walk you through parts of AP problems, but then to get that extra 10% in your test scores, you're going to need to finish all the AP problems. And let's go move on to question 3. Okay, question 3 is another short FRQ. So what we have here is the first ionization energy of magnesium samples found on Earth is experimentally determined to be 736 kilojoules per mole. If a similar experience is conducted to determine the first ionization energy of magnesium in the rock sample from another planet, will it be greater than, less than, or equal to the first ionization energy of magnesium found on Earth? Explain your reasoning. So what the big idea here is, we have to think about the properties, okay, of ionization energy. Like, what is ionization energy? Well, first of all, ionization energy is the energy it takes to ionize or remove an electron, create an unequal amount of protons to electrons. The only difference between Earth and another planet would probably be one, the gravitational force experienced. Yes, the environment, but very, very rarely does the environment affect the characteristic of the atom itself. All right. And gravity doesn't really have anything to do with the atom at this point, in terms of it's not going to like make the atom heavier at a measurable level. So what we would say is equal to, we would say that the first ionizations would be equal to, okay, that on Earth. Because, okay, the protons and electrons remain the same, right? For neutral magnesium to be neutral magnesium on another planet, you still have to have the same identifying characteristics. And the protons and electrons being the same means that the Coulombic attraction would also be the same. So the energy required to remove an electron would also be the same. So equal to that on Earth, because the protons and electrons remain the same, therefore resulting in the same Coulombic attractions and ionization energy required. Okay. So how about D? D, a table of successive ionization energies for magnesium and an unknown element is shown below. Predict the identity of the unknown element. So remember that when we talk about ionization energies, one, you know that every time we remove sequentially, as we sequentially remove electrons, it's very unfavorable. It becomes more and more unfavorable. It becomes more and more energy requiring because the element starts to be like, okay, that's enough. But we also know that some elements like magnesium, like your alkali and alkaline, actually like to have it be removed. So there's a lower ionization energy. It still takes some energy because you're still overcoming Coulombic attraction, but not as much. It's pretty easy. And once they reach an octet, once they're isoelectronic with a noble gas, then they start getting really desperate to hold on to those electrons. So you'll see a giant jump between the successive ionization energies if you've hit octet and you're about to ruin the octet. You're about to disturb the octet. So what we see here is for magnesium, the first and second are relatively low ionization energies, right? And then after the second ionization energy, you are now at the point where you're going to disturb the octet that has now been reached. And so the third ionization energy would push magnesium into a no longer octet electron configuration, which is why the third ionization energy is giant. So then we look below and we see, okay, this unknown element seems to demonstrate a similar, okay, a similar tendency. However, the jump here is between the first and the second, okay, the first and the second. So what we see is, okay, that whatever this unknown element is, it must be okay, relatively speaking. It must be pretty okay with losing one electron, but not losing any more electrons after that. So that means that we know between here and here, we've reached an octet. So we know that we don't want to disturb the octet. So when we look at the periodic table, any alkali, column 1, okay, element could be this unknown element. So we could choose anyone. We could just say sodium. You could say lithium, really, but that is kind of the big idea right here. So that is that question. I think we have one more to go through. Let's scroll on down. Again, 4, you will be, tomorrow we'll look at 4. But here we are. This is the one that I wanted. Question 5, short FRQ. And I think that's the last one I'm going to go through today. Consider the element in the periodic table that is directly to the right of the element identified in part A. So we identified the element in part A for question number 5, short FRQ, as phosphorus. And now we need to consider, okay, the element directly to the right. So on the periodic table, the element directly to the right is sulfur. Okay, sulfur. Identifying part A, would the 1s peak of this element appear to the left or the right or in the same position as the peak of the element in part A? So what we're doing is we're going to just hone in on the 1s, okay? I'm going to say to myself, well, 1s is at a high binding energy because it's super, super close to the nucleus, which means the 1s orbital is always going to be, the 1s orbital electrons are always going to be the hardest to eject, which means they're going to have the greatest binding energy, which means they're going to be more to the left according to this photoelectron spectrum, where our x-axis decreases as we go to the right. And so we know that when we look at sulfur and phosphorus, okay, one, yes, sulfur has gained an electron, but we also know sulfur has gained one more proton compared to phosphorus. And we know that in a lot of ways, the Coulombic attraction is mainly driven by distance and proton count. Electrons are kind of just there for experiencing it. So we've gained one more proton, and that is a massive impact. So what we would see is that our Coulombic attraction has increased. So when we look at when we compare the two electrons in the 1s orbital of phosphorus, and we compare the two electrons in the 1s orbital of sulfur, what we see is that the two electrons in the 1s orbital of sulfur would experience, okay, the two electrons in 1s orbital of sulfur would experience a greater Coulombic attraction due to more protons, and thus, okay, and thus have greater binding energy, making or resulting in the 1s peak being to the left, or a higher energy level on the spectrum. Okay. So if you want to be even more specific, you could say, right, more protons 16, right? 16 instead of 15. And yeah, so that's the end of today. I may or may not check tomorrow. And I think you guys have one more video to watch tonight. So on the mole. So best of luck and have a great one.